All right, up next, we're going to look at what we call some common logarithms. So there's a couple sort of go-to log examples, and we're going to look at some inverse log properties. And I think I'm actually going to do the inverse properties first, because they're somewhat useful when we're talking about these common logs. So let me set these inverse properties up first. So inverse, right, is sort of means reverse, and so it's in some sense a little bit of an undoing. And so this is part of the relationship between logarithms and exponential functions. So in general, we would say that like f of x equals b to the x is an inverse function to g of x, which would look like the log base b of x. So these two functions are essentially doing opposite things relative to each other. The sort of y and x values are sort of flipped back and forth. So you have sort of the same pairs, but the role between x and y is flipping. We'll do some graphs in a different video to sort of illustrate this a little bit more. You can visualize it. But just algebraically, we're going to say they're sort of inverse functions. They have this relationship. This gives us a couple different properties. So it gives us a couple special properties where if we sort of combine logarithms with different exponential setups, the log and the exponent and the log and the sort of exponential aspect end up canceling each other out. So special property number one is going to look like if we do the log base b of b raised to the x. What happens here is the logarithm and the sort of base value b end up canceling each other out, and we're just left with the x that's in the exponent. This is, almost a property that we've essentially done individually in an example, right? We did an example that kind of illustrated this earlier in one of the videos, and it makes sense, right? The sort of idea is, okay, b is the base value. How do I get from b to like b to the x? What's the exponent? I mean, the x is sort of sitting right there in the exponent value. You can imagine the sort of LeBron James meme where he's pointing right at the x. The exponent is right there. Thank you, LeBron James. We see it. So how do I get from b to the x? Well, the power has to be x. It's the only thing that makes sense. So in this way, the sort of logarithm and the exponential sort of setup in some sense cancel each other out, and we're just left with the power where the variable is. The one that's a little bit less intuitive is if I sort of reverse the roles here, and if I have b as a base value and I raise it to the log base b of x. So this is, I have some base number and I sort of raise it up to the logarithm base b of x. So this is a little bit trickier to unpack, right? The idea is, okay, so b is the base value, log base b of x, so that's the exponent, that if I put it onto b, I would end up at x. So then if I take that particular power, put it onto b the base, kind of by definition, I should be ending up at x. That one just looks weirder, honestly. It just kind of looks strange. The first one is maybe a little bit more intuitive, and you can sort of think your way through it a little bit easier. In theory, though, they both are sort of inverses, right? They both are sort of undoing the operations, and they're sort of leaving us with this x value. So let's take these two sort of special inverse properties, sort of put them in our back pocket, and let's introduce a couple common log base values. Common logarithms. So the first one is going to be log base 10. And the idea is if I have a logarithm that's log base 10. So 10 is my base. So obviously, like, 10 squared is 100, 10 cubed is 1,000, 10 to the 4 is 10,000, 10 to the negative 1 is 1/10, 10 to the negative 2 is 1 over 100, 10 to the 0 is 1. All these different powers of 10, right? So those would be my x values, the power, right? The exponent itself would be sort of the result of the log. So this is a common base, and so what we're going to use is we're literally just going to say log. So if we just write log and we don't write a base number, so the assumption is not that it's like a choose your own adventure type number. The assumption is that it's base 10. So for example, right, if I just say, okay, log of 100, how do I get from the implied 10 to 100? What's the exponent? 10 squared is 100, so the exponent is 2. How do I get from log, let's do 1 over 100. How do I get from a log that's implied to be base 10 to 1 over 100? So 10 squared is 100. If it's 1 over 10, it must be negative 2. So the idea here is, right, a log with no number written, and it's the full log log. The implied base value is base 10. On a calculator, there's usually a log button, and it doesn't mean, right, pick your base. It's specifically log base 10. So your calculator will do base 10 logs usually. The other log they will do is what we call the natural log. And so this is log base e. Remember e. E is our sort of natural exponential base, right? We sort of said e to the x is going to be kind of our sort of go-to exponential function. So e is also then going to be sort of a natural base for our logarithms. The exponentials and the logarithms, right, kind of relate to each other. They go back and forth. And so what is this going to look like? Well, the whole idea, if we call this the natural base value, so this also then would be the natural log value. So how are we going to write natural log? Well, obviously what we're going to do is we're going to write L and then N of x. So natural log spelled L and then N. I sometimes jokingly refer to this as log natural. I'm sure in maybe French, let's say, in a different language that wasn't necessarily English when they introduced this, probably ln made a little bit more sense. We call it the natural log. You could make a very convincing argument that it should be nl for natural log, and yet here we are. The log takes precedence, I guess. So the L comes first, and we get natural log is ln of x, and so this means the log base e of x. And the natural log is that. It really is going to be the log value that we use probably more often than not, especially if you end up going and doing calculus. The natural log is, maybe the only log you're going to see most of the time. What this means as far as different examples go, well, because e itself is not particularly a great number to work with, it means that we would sort of have trivial things like the natural log of e. How do I get from base e to e? Would have to be 1, right? You could do things like the natural log of e cubed. If the base is e, how do I get to e cubed? LeBron meme. It's right there. The exponent is right there. Right? The exponent is 3, so this must be 3. This starts to tie in a little bit with some of our log properties, right? If the log base b of b to the x is x, we're sort of seeing that, right? The log base e of e cubed, right? The sort of log and the e here are in some sense canceling each other out. If we did something like natural log of root of e, that really means the natural log of e to the 1/2, right? The root is a 1/2 power. And so the idea here is, okay, our sort of inverse properties take over. You can also reason it out and say, how do I get from base e to e to the 1/2? The power must have been 1/2. This kind of a thing. If we want to play a little bit with this other form, right? So b raised to the log base b of x. Now's a good time to do it. I suppose we could take something like e, raise it to the sort of natural log of 6. And what this means is, so e raised to the number, where if we put that number as an exponent on e, we would end up at 6. E and 6 don't have a particularly close relationship, right? E is this sort of decimal around 2.718. Not a super close relationship to the number 6 by any means necessarily, but if I take e and I raise it to natural log 6, that's going to get me back to this 6. So the e and the natural log are these sort of, right, have this inverse relationship, and in the right setup will sort of cancel each other out. And it will do things like this. In theory, we could do a similar thing here if I did something like 10 raised to the log of 15, right? So writing the log with no base value, the base value is implied to be 10, so 10 to whatever it is that you would put on a 10 to get to 15. We're kind of ignoring and stepping over, well, what this actual number would be. In theory, right, it's whatever number it would take to get us from 10 to 15. That log would be it. You could use a calculator to get the decimal version, but if we end up with this setup, we're just going to be content to say they cancel each other out. It's this nice inverse property, and we're just going to end up right at 15. So that's a couple special inverse properties and what they would look like on our common logarithms.